Now, that was part number one of how to address autocorrelation. Part number two is pre-whitening. Or rather, today, either you do pre-whitening or you don't do anything. And I'll get back to this point in a few slides. Now, the idea with FSL is the following. They say, look, if we only knew what those off-diagonal elements looked like, so what the matrix V looked like, then we could get rid of it, right? Because if we know V, we could find another matrix, W, such that if we did WV, W transpose, it would give us exactly the identity matrix. And now our variance covariance matrix would again be sigma squared I, sigma squared identity matrix. Right, because then what we would do is, if we could find this W that had this property, then we would just pre-multiply the whole GLM by W, and it would look like this. Instead of having Y equals X beta, we would have WY equals WX beta and WE, where E is the, where E is the structure and then the well-behaved error term. So if we knew this, right, then if you calculate the variance for this, it turns out that the variance is sigma squared W V W transpose, which means by design, as we said here, since we picked W so that we get this, it means that in the end, our variance, the variance of WY of the whitened time series, is now sigma squared I. So in other words, if we know what V is, if we know what that structure is, we can clean it off. And now we're back to having the well-behaved, and now we're back to having our blue estimator, because our time series no longer has autocorrelation. Now, the problem, however, is that we don't know what V is. We don't know what that structure what is that correlation between errors at different time points. So FSL uses a 4-step pre-whitening procedure to find it out, or to approximate it best it can. First, run a regression under the infringed Gauss-Markov assumptions. And then you never look at the betas that you get. All you do is you take the residuals, and then you try to find out in the residuals what is V. Because if I can find out V, I can then create W such that sigma squared W V W transpose equals sigma squared identity matrix. And so indeed, if I can find V, I can determine W such that if I pre-multiply the GLM by W, then I've whitened the data. Once I've done that, now I can run a second regression on the whitened data, and what I would get is the blue estimator. So I'm back to having my my best linear unbiased estimator. So how do you do this? Well, we run a regression, and now let's take the residuals of that regression and see how we would derive the correlation structure. It's fairly simple, really. We would estimate the autocorrelation structure for each voxel as follows. We take the residuals, right? So these are the residuals at each time point, right? Volume 1, volume 2, volume 3, volume 4, etc. You create an exact copy of it, and you lag it by 1, right? And then what you do is you take the correlation of this vector and this vector. And that gives you the correlation between the error time point 1 and the error time point 2. And then you do the same for lag 2. And that gives you the correlation between the error time point 1 and the error time point 3. And then at lag 3, and lag 4, and lag 5, and lag 6, and lag 9, and lag 10. Notice, however, that the further away the lags, the fewer the data we have in order to calculate this correlation, right? We started here with having 11 time points to calculate the correlation. The further away we went, we ended up having only 2 points to calculate the correlation. So obviously these correlations, the further away, like the correlation between time point 1 and time point 10 is actually not very well estimated. It's not very reliable. Indeed, what we will then do is two ways of regularizing the data. First, we spatially regularize it in the sense we smooth the estimates of the autocorrelation across different voxels. After all, if voxels are nearby, they probably have the same structure of autocorrelation. So it makes sense to smooth it spatially, and this we refer to as regularization. Then we apply what is known as a Tukey taper. And this essentially is a smoothing, but in time instead of in space. So point number 2 smooths in space the estimates. Point number 3 smooths them in time using a Tukey taper. Now, Tukey taper looks sort of menacing, written this way, but all it's saying is this. Keep the autocorrelation estimate up to a certain number m, which in our case will be, I guess, 8. After lag 8, so the Tukey taper says after lag 8, just set the correlation to 0. See the dashed line. The real correlations is the continuous line, but see how it becomes unstable? And it makes sense that it becomes unstable because we have fewer and fewer time points to estimate it. So the Tukey taper says, look, keep the autocorrelation estimate up to a certain number m. Go back to that. If the volumes are below m, then you keep what you estimated, but at and above distance m between different volumes, between different errors, then set it to 0, okay, which is again what you're seeing here. Okay, so we first estimate the autocorrelation structure, and then we regularize, we smooth it spatially and temporally. And finally, we pre-multiply the GLM by W, we find W, we pre-multiply the GLM by W, and now we just run a new regression, and what we're getting is the best linear unbiased estimator. Of course, under the assumption that this procedure has allowed us to recover well the actual structure of V. So we're assuming that we did a good job at finding out what V is. Now, SPM uses a completely opposite approach. And you've heard me say this before, SPM and FSL are just philosophically different. FSL likes going into the data and finding out what is what. For example, we went into the data right now to find out V so that we could create W. SPM, on the other hand, says, look, we don't need to go in the data and look at it. We know what autocorrelation structure, more or less, looks like. And it's best modeled by a global autoregressive one model with a correlation of 0.2 plus some white noise. In other words, what they're saying is, look, so the variance covariance matrix, the off-diagonal elements, so the structure that you're likely to find in an fMRI experiment, always kind of looks like this. You can scale it with lambda 1 and lambda 2, with these two parameters. But we know what the off-diagonal elements look like, because they look like an AR1, a global AR1. So you apply the same structure to all of the brain. You say every single voxel in the brain probably has an autocorrelation structure that kind of looks like this. So I don't need to go inside my data and calculate it like FSL does. FSL goes in and calculates it for every single voxel. SPM just says, it probably looks something like this. And then you just estimate these two parameters. The shape of it, which is these off-diagonal elements, you already know that. Now, does this matter? Turns out, Lenoski and colleagues looked into different algorithms to whiten the data. For example, the FSL one and the SPM one. Turns out it makes a great difference. Now, I should say, one thing you can do is you can just ignore this. See, you'll remember that I told you that the problem with autocorrelation is that the betas themselves are still fine and unbiased. What's affected is the variance estimate. That is now biased. But see, some software never gets to use those first level variances. Typically what you do is you would take the estimated beta, you would carry that forward into a group analysis, and then run your group analysis on the beta. In this sense, you haven't used the variance of the beta from the first level. So who cares if it's biased? And that used to be the approach of AFNI. Now they allow you to do something more sophisticated. And so what this graph is showing is on the x-axis, you're seeing different algorithms. And this one here is the OLS, so where you just ignore it, which is what AFNI used to do. And on the y-axis, it's telling you what percentage of voxels are white. In other words, how well have we whitened our data? AFNI just ignores it. So this tells you that on average, if you take a data set, you have between 20 and 40% at most of white voxels. All the other voxels are colored, and you have to do something about, sorry, excuse me. All the other voxels are autocorrelated, and you have to do something about it. Now, if you do something like what SPM does, which is this regularized AR1, it turns out that it cleans only 60% of your voxels. But there's still another 40% of voxels that are still not clean and still have autocorrelation. And the problem with the SPM approach is that you're applying the exact same structure to all of the brain, to every single voxel in the brain. Turns out that's actually not optimal in the sense it doesn't fit quite as well every single voxel. On the other hand, this NP down here is what FSL does. And as you can see, it does an excellent job. We're really between 99 and 100% cleaning. Okay, so let's do this last step. So here we are. This is where we had left it at with the high-pass filter. And now last thing, we're going to do pre-whitening. And you can't really see it in the data. You would see it in the residuals, right? The data itself is the same. However, you will see that it does affect our t-stat, which went down again, right? Our effect size went down, the variance went down, and overall our t-stat went down. And I know you would say, well, but I want my t-stat to be large. But the truth is that you want your t-stat to be accurate and to be valid. And so all of this allowed us to reach a point where our estimates, and therefore whatever testing we do on them, are reliable and valid. Right, and that's it for the first level analysis. I'm putting here as the last slide a number of resources that if you are interested in this, you might find helpful. I wrote a paper in 2011 covering these things. The aim of that paper was to try to write in English, or sufficiently in English, these complicated matters, because the original literature is written mostly for biostatisticians. And then I added a few books that are particularly good. There's the 2001 handbook by Paul Druck, Mumford, and Nichols. It's a pretty good book. I have to admit, not my favorite, but it's a pretty good book, and it's an excellent introduction. It's easy to read. Then, if you really care about the GLM itself, there is this wonderful book by Lazar, which is the statistical analysis of functional MRI data. And then if you really want to understand MRI analysis, fMRI analysis into detail, and you want to look at all the various aspects of it, the best thing you could ever read is the SPM, the Statistical Parametric Mapping, as its own Bible. And what we cover today is in one specific chapter, but this book right here contains everything related to fMRI analysis. If you can read through the book and understand it, you really understand fMRI analysis in depth.